All right, everyone. Welcome to today's Energy Symposium, sponsored by the Energy Institute. Next week is spring break on campus. There will be no talk on March 17th. The talk on March 24th, 2 weeks from now, will be Tim Latimer, who's co-founder and CEO of Fervo Energy. They're a local company looking into geothermal power, so he's going to tell us the latest and greatest about generating electricity from geothermal resources. Today we have a remote talk here from Costa Samaras. Costa is an associate professor of the Department of Civil and Environmental Engineering at Carnegie Mellon University, and he's also an affiliated faculty in the Energy Science, Technology, and Policy program, also at Carnegie Mellon University. So he does a lot of research on energy systems in general, climate change, automation, and defense analysis. And today he's going to give us a talk about electric vehicles and autonomous vehicles in the context of decarbonizing. So Costa, are you on and ready to go?
I am, thank you.
Okay, we hear you well. If anyone has a question during the presentation, you can try to raise your hand and maybe say question, and I can bring the microphone to you. Otherwise, we'll have questions at the end. So Costa, take it away. Thanks.
Well, thank you, Kerry, and thank you to the UT Energy Institute and to Professor Josh Busby for the invitation to talk to you all today. I'm very grateful. I know it's the week before spring break. I hope everyone is staying safe and healthy and informed with the ongoing and deepening coronavirus crisis. Today we're going to talk about electric and driverless transportation and give us some insight on some of the research that the students and I have been working on with some faculty collaborators over the last couple of years with some implications in current energy policy. So of course the students both at the undergraduate and graduate level are the talent here, and I always acknowledge them up front. I have a group that works in transportation, transitions, and automation, and I have another group that works in climate resilience and energy, and we kind of overlap when we can. And then I'm fortunate at Carnegie Mellon and beyond to have a whole host of faculty collaborators and co-advisors for our students. So this is a pollution control technology device from days of yore, and this is here in Pittsburgh. But if you go to any pre-car cities, you'll see this pollution control technology device. And the point of this is that when you're walking around all day and you're about to walk into your house, right, this is the step right before you get into your house, you probably were walking in horse poo because transportation in the late 1800s, both freight and personal, was largely horse-driven. And with 180,000 horses in Manhattan and Brooklyn in the late 1800s, each producing about 30 pounds of manure per day, there was an entire fuel ecosystem of feeding, caring, and removing, feeding and caring for horses and then removing manure from the streets. So this pollution control device was to remove, I don't know, 40 to 90% of the horse poo off your shoe before you start walking in the house. And so when we transitioned to leaded carbon dioxide filled gasoline smoke, it was seen as a miracle cure for some real problems in dense urban areas at that time. Now we have another challenge, and that is to dramatically bring global greenhouse gas emissions close to zero and then probably below zero. In order to stabilize global temperatures at 1.5 or 2 degrees C. As the analyst in the room will recognize, the gradient descent and the slope of these curves gets larger every year that we are not mitigating. So starting back in 2000, it would have required some decarbonization rate of about 4%. Starting now, the rates are pretty heroic. But we are going to continue to make plans and progress on decarbonization because every degree matters and every ton matters. And part of that is dealing with transportation. Now, transportation is the largest greenhouse gas emissions sector in the United States. And it's something that is growing pretty rapidly around the world as countries get richer. More people are wanting and choosing mobility, and some of that is through the personal automobile. Now, we should, we, the global community, should want mobility to increase around the world. It enables opportunity, and it enables access, it enables leisure, and it enables economic opportunities. We have to figure out how to make it very low carbon. Now, one of the challenges in the United States, and of course correlated around the world, but this is focused on the US, is just how big the transportation decarbonization challenge is. So this is a chart we made for all the transportation greenhouse gas emission sources in the US. So blue on the bottom is cars and SUVs, red is jet fuel, yellow is freight from trucking. You'll see a little natural gas pipeline on the top, and that is the compression stations of moving natural gas, and that is counted in the transportation sector because it pipelines transportation. But the big sectors, blue, red, yellow. If we want an 80% reduction in transportation emissions below 2005 levels, which used to be kind of like where we wanted to be, and that was an important goal 5 to 15 years ago. And now, because of that steep of that curve that I showed you on the first slide, now we're going to have to get to 90 or even 100% below. But let's assume we want the old goal of 80% below 2005 emissions. We have to squish all this activity below that dotted line. And that means we have to deal with cars. And so how do we deal with cars? Well, we deal with cars by either changing the vehicle technology, making it more efficient. We change the fuel, or we change the total vehicle miles traveled. Now, electric cars are one way that we can change both the technology and the fuel. And as Carrie and I will tell you, we have gotten this question, but what if it's charged on coal our entire lives? Well, even when it's charged on coal, it's that 900 grams per CO2 kilowatt hour here in the first bigger green bar. It's better than the current fleet of cars. Now, it's not better than a hybrid, but that 40 mpg car, but it's better than the rest of the cars. Now, if we charge, and it's pretty unlikely that we're going to hook up a electric vehicle to one individual coal plant. The grid, as we all know, is a collection of regional power plants. But if we charge it with electricity that look like coal, it looks like this. If we charge it with electricity that looks like an efficient gas plant, it might look like this. So electricity charged on gas basically beats most hybrids. And as the electricity sector decarbonizes further, that only gets better. So what we, Carrie and I and others who've been working in EVs for a while have been banging on the drum saying, let's get emissions from the electric sector down to zero to really get the biggest bang for our buck for electric vehicles. But we can pause on the what if it's charged with coal and think about some of the other issues that we need to talk about today. So electric vehicle, even charged on on all renewables and nuclear and hydrogen, still have impacts. So this is the Cybertruck running with Elon Musk driving, running over a child-sized bollard there, a sign there as it leaves the parking lot. So even when we're charging on zero life cycle emission electricity, there are social costs of driving. And so all the emissions-related costs, emissions and oil-related costs are on the left, air pollution and climate change and oil security. But the ones in color in the middle, congestion and crashes and a little bit of noise, really make up a big portion of the social cost of transportation. These are the values used by NHTSA and EPA when they create fuel economy standards. And so these are the values used in cost-benefit analysis by the government. And the government there are ranges that we can put on all these, and we do a lot of work on that as well. But congestion and crashes are not solved by EVs alone. luckily, there's a whole suite of new technologies that include automation, both in the personal vehicle, but also in micromobility, IT-enabled sharing, IT-enabled robotic delivery, a lot of ways that new technology can change the way that cars both operate and are used. Now, a robocar senses the world around it, and it plans on what to do, and then it makes a decision. So this is Carnegie Mellon's robocar. It's a little bit old now. This is from 2012. This vehicle is driven across the country autonomously with the driver in place. You see that big red button. That's to smash it in case you're about to run off the road. The technology is not good enough for this car to go across the country by itself, and we would feel okay with that, we, the robocar community. And so it's important to understand that there's a whole spectrum of automation. This is, SAE, the engineering organization, put together a list of automation levels 0 through 5, and there was a lot of words on the screen, and so I made them all into emojis that I can understand. And a driver assist, that's level 1 car, is we're driving, the robot's helping us do a little bit better. This is when you have front-end collision avoidance braking or notification. If you have a newer car and you try to change lanes and a little light comes on your mirror telling you, hey, there's somebody in your lane, that's a driver assist. The robot's making us a better driver. As we move up to level 2, the robot is in control, but we're really also driving, right? And that is hands off, feet off on the highway. Car is maintaining speed, maintaining lane, but we're in charge. Somebody darts out, somebody slams on their brakes, something goes wrong, we're still in charge. One of the challenges is this level 3. And so level 3 is punch in an address and the robot takes you there. They're in charge, but you have to be immediately responsive in a backup incident. And we as humans are just terrible at doing this. We saw this in the Uber crash in Arizona. This is something that the industry is kind of testing right now, but a lot of analysts are feeling like this is probably the most dangerous hump in this automation curve, is that we are not good at waking up from a distracted slumber. And if we have to be the backup drivers, that's not great. And then level 4 and level 5 is really the kind of the better situations where we are still in the loop in level 4 only when the machine leaves a operational design domain. That operational design domain could be the entire city of Austin, maybe it's a county, maybe it's a whole state. But there's going to be places in the country where the machine can't go. And level 5, full automation, is basically car can go anywhere by itself anytime. And that might be a decade away, it might be 4 decades away. Really, level 4 is where we start to get the big benefits of automation. And we're still working on getting to both level 4 and level 5 at any level of vehicle that we would want to see for sale. Now, there's a lot of videos, if you go on YouTube and you look at kind of like Tesla fails, a lot of videos like this where this was an actual actor staging this, but people are falling asleep and letting the Tesla drive it. That is completely dangerous, not at all how the technology is supposed to be used. And please do not do this. I think the problem with the branding here is that Tesla called this autopilot. Really, Tesla is a level 2 vehicle, right? It's not even halfway through that spectrum. It's great. The technology is wonderful, and we should all continue to use it. But it's not in any way, shape, or form a self-driving vehicle. Now, what level 1 and level 2 automation does do is enable us to be much better drivers. I mentioned that front-end collision avoidance, lane keeping, and lane departure warning. Those are technologies that really can save a lot of crashes, and you don't need to have a Tesla to get these. You can buy this on a Honda Civic or a Toyota Corolla this afternoon, and you should, because some of our research has found that if every vehicle in the country had these 3 technologies and they worked perfectly, we could save about 1.6 million crashes, including 7,200 fatalities. These all have real social costs. in the tens to even hundreds of billions of dollars. And so it's, from a benefit cost perspective, the little paper that we did there, we did a couple of these, like we don't have to wait for fully driverless vehicles to get the safety benefits of automation. And we should start deploying these immediately. Now, when you have these level 1 and 2 costs, you also can save some fuel. And you can save fuel by reducing some of the congestion associated with crashes, if you're reducing crashes, but also from adaptive cruise control, you're driving smoothly, you're not jamming on the accelerator, from dynamic route guidance, and from some platooning, we could save, let's call it 10%, but it's a range, 6 to 23% of fuel use just by these level 1 and 2 technologies that we could get now if they were more widely spread. But as we transition to these level 4 and above technologies, we really have to think about how this changes the transportation ecosystem. I put pictures of our graduate students that are working on these issues on these slides so that I'm giving them some credit, or giving them the credit. So we're thinking about how do people use these vehicles, and then how does that use affect energy use? Are there going to be some shared autonomous shuttle, or is it going to be, I need to get to DC, and DC from Pittsburgh is about a 4.5-hour drive, and I could get in this autonomous machine on the right and have it drive around the Beltway overnight while I watch Netflix, and then I'll get up and take my morning and then meeting, and then I come home. There's ways that vehicle miles traveled, VMT, will increase, and there's ways that vehicle miles traveled will decrease with autonomous vehicles. And nobody who's credible knows the sign of that yet. We don't know if people are going to own these or they're going to share. The kind of the hyperloop, or the loop concept that was really initially for kind of public transit pods. There's always been talk about what it would actually be used for, but Musk has said we're going to put vehicles on skates and we're going to bring them up through elevators, and this looks a lot like a private vehicle system. Or they could be kind of shared vehicles on the road. We also don't know that they're going to be all electric. That is one given that we think that we know, but we and others have done some work, and my colleagues here have a paper coming out on this, and I'm not sure when it's going to be out. But they have basically made some estimates of the drag from the additional LiDAR and the use of the computer and the GPUs really to run the processing system on board the robocar, burn down your electric vehicle range. And so maybe from a vehicle design perspective, the most optimal platform for a robocar is going to be some sort of plug-in hybrid, or maybe even just a gas car. And so we can't take for granted that it's going to be electric. We hope it is, but we have to, this is going to require some policy and some incentive. We also are looking at how shared AV shuttles could help increase transit equity and serve demand. This is Pittsburgh, Allegheny County. All of the purple census block groups are areas that are equity designated, have low socioeconomic status, but also don't have a lot of transit service, largely because they have fairly low population density. And so some shared electric shuttle could potentially serve these low population kind of exurban areas more cost efficiently than a big bus. All right, so those are some ways that electric and automated vehicles are interact in the transportation system. Let's get back to decarbonizing. Now, I just told you that vehicle efficiency technology could go up or down, depending on if it's a smoother drive, or if the car's brain eats up a lot of the electric range. We hope that the carbon intensity of the fuels is going down as we go to electricity, but really the total VMT, the total vehicle miles travel sign, is really on both sides of zero. So we need to model all of these factors under some range of uncertainty, and come up with policies that enable a transition to a very low carbon transportation system in spite of this uncertainty. So I'll give you an example of how some of this might work. This is Seattle, and Seattle has a dense downtown, as you see in the middle, and then neighborhoods all around it. Pittsburgh is very similar. And In the neighborhoods, there's permit parking, but there's also a lot of free parking. And Seattle has fairly expensive parking rates downtown, and then relatively free or actually totally free parking in the neighborhoods. And so this is the baseline parking occupancy rates that we get from Seattle's parking office. And downtown weekday parking rates are pretty full. It might cost $20 to $30 per day to park downtown, and it's free to park in the neighborhoods. You can see what's coming, right? We envision this paper as basically, let's model how a downtown empties out and with robocars. And Seattle is a perfect example. It's not that far from downtown to the neighborhoods, and the neighborhoods currently are free. Now, the neighborhoods might change their pricing, but currently they are free. So if I had a robocar that would drop me off downtown and then drive and find the first freest parking, with 25% of the fleet being robocars, the first ring of neighborhoods the streets would fill with robocars. And maybe you would send enforcement vehicles out, but we think that the robocars, we could program them to move on the other side of the street when they tell each other that the parking enforcement officer is coming. So as we get more and more AVs into the fleet, now nobody parks downtown. All the vehicles are parking in the neighborhoods. We've introduced a whole bunch of new vehicle miles traveled throughout these streets. We've increased energy use, but we've also maybe reclaimed some acres downtown. Maybe all of these parking garages could be housing, could be retail, could be office, could be parks. We have made a big dent in the annual parking revenue of downtown Seattle. But this is an issue that shows what happens with private AVs. And we have to think about how we might change induce private AVs to be shared. And there's a paper on that. If we want decarbonized mobility services, right, that's really what we want. We don't really care about miles. We don't really care about type of car. We want mobility that is free from carbon. And if we want an 80 to 90 to 100% reduction in light duty vehicle, that's cars and SUVs, of CO2 by mid-century, we will need the total amount of CO2 from the light duty fleet in 2050 would need to be about 250 million metric tons. Right? So I'm just trying to do the math and say, what are some reasonable targets that we could put on transportation decarbonization to think about how do we get there? And if we were going to do 90%, we'd be in low 100s, let's say 125. So what we've done is build an open model of the U.S. light-duty transportation sector. This includes the vehicle stock, the travel bounds, what the grid looks like, and how many, what the MPG of the regular fleet, what the MPG of the EV fleet looks like, and then we can come up with some total CO2. This is we will make all of this public, and we're going to publish a paper on the modeling framework. We're hoping to make just basically, we will make all this modeling public so that everybody doesn't have to recreate it all the time. We found that we were basically redoing this exercise with every couple students, and so we're just going to do it once and build on it. So under some base case, and there's a whole bunch of conditions that we need to meet in order to make electric vehicles and automated vehicles be a force for decarbonization in the transportation sector. And I'm going to walk through a bunch of those conditions. The headline is, in case you have to leave, is there's a path, and we're going to find that path, and we're going to emphasize the way to do it. But here's the first piece. So in 2050, we have total light-duty vehicle CO2 on the x-axis, and how carbon intensive the grid is on the y-axis. Now, our current grid in the United States is about 440 grams of CO2 per kilowatt hour, so really double where we're at up here. But I'm assuming in 2050, we're, the highest we're going to be is 200. If it's not, then we have other problems. But let's say we want to get to our 80% carbon reduction target, right? Our 80% carbon reduction target is right here, this line, 250 million metric tons. That means that anywhere in this space meets our target. So we can have all the way up to a 200 gram CO2 level and some amount of miles that are from EVs. So under a base case, though, if we get our CO2 all the way down to 0, right, I can come over and read that this says we need 67% of our miles to be electric. Doesn't have to be 67% of the cars. 67% of the travel has to be electric in 2050 to reach an 80% reduction target. Same thing for 90%, except now my opportunity window shrinks. Now I'm up at about 84% of the fleet has to be electric with a zero carbon electricity sector to meet a 90% carbon reduction target. Now as we float up, and as you know, 0 is a very, very low number in anything, but also in the electric sector. And so maybe we're going to get to 50, right? So if we get to 50, now all of a sudden we've gone from 84% miles to maybe 87% miles. You can see where this is going. As you increase the CO2 in the electric sector, we need more and more of the miles to be electric in order to make this work, because the rest of the miles are traveling on gasoline. So what we've established is that is for the current projected amount of travel. Now, nobody says that travel has to remain the same. We travel about 3.2 trillion vehicle miles traveled a year in the United States. Passenger travel of that is about 2.9 to say, let's call it 3. So current passenger travel in the United States is about 3 trillion vehicle miles traveled a year. In 2050, EIA, and we take EIA, we love EIA, we take them with a grain of salt, we use that as a starting point, but let's assume that they're right, that EIA says that in 2050, total travel is not going to go up too much, it'll go from 3 trillion to 3.3 trillion or 3.4 trillion. What that means is that as travel goes from 3.3 either up or down, our amount of EVs that we need also go up or down. And we can use this travel budget frontier as a proxy for the uncertainty in robocar or Uber and Lyft related additional miles. So if, I remember I said for a 90% target, we need around 84, 83% EVs. Well, if robocars and Uber and Lyft makes us drive a lot more, 4 trillion vehicle miles travel, now we need more EVs. If we somehow drop total travel to the level it was in 1991, 2000, or 2 trillion VMT, now we need fewer EVs on the road. So this space bounds how our solution set and how we might deal with policy, as well as the design of transportation incentives to deal with getting in this case, a 90% target. This is an 80% target. So remember, 80% target, not really that good enough, but imagine that we really want to deal with an 80% reduction. We need 63% EVs if we have 3 trillion vehicle miles traveled. We need 73% EVs if we have 4 trillion vehicle miles traveled. And then if we reduce a bunch, we only need half the fleet to be EVs. But take a look at this number. Oh, the number didn't pop up. This number. So I mentioned that we have 3 trillion vehicle miles traveled total. About 70% of that is in urban areas. Now, urban is pretty loose in this context. It's defined by DOT. We might recognize urban areas as suburban or even exurban, but they're not rural. So an entire metro area might be counted as urban, even though it looks pretty rural. But because a decent portion of the VMT is in urban areas, we might be able to have some sharing. And what sharing could potentially do is keep passenger miles traveled the same or even increase it while reducing vehicle miles traveled. And so what this 2200 line is the amount of VMT if we completely eliminated the urban VMT from the top 10 most populous states, and that's Texas is in there, but that's about 1 trillion of our 3 trillion VMT currently comes from these 10 states. So it gives us a little bit of a bound of where we would need to be if we could, all tomorrow everybody is riding a bike in every one of these urban areas. we would reduce the amount of EVs we need in the fleet still to about half by 2050. Better than 63, but a heroic attempt. We also could increase the load factor. Now, what's the load factor? It's how many people are driving in a car for each mile. So right now, on average, the load factor in the US is about 1.6. And so there's a lot of solo trips, but there's also a lot of trips when lots of people in the car. Now, what this chart is basically showing us is that if we increase the load factor, we can meet our 90% target a little bit easier with fewer EVs. But really, the increase in the load factor only buys you so much. Really, the better benefit is electrifying. Right? We should increase load factor, but if we electrify, if we go from 75% of the fleet to 100%, we can have a much lower CO2 footprint. And as I mentioned, this target here assumes that people are if they shift from car to a bus, that bus is also traveling in electrified and in a zero carbon environment. If everybody shifts to a diesel bus, we'll have to add that carbon back in, and then our miles budget's going to move a little bit this way. Now, I know, this is an Energy Institute. Everybody's familiar with grid modeling and understanding the grid. We don't charge vehicles with a static, uniform, average national grid. The reason that we presented this in this way is to show the kind of the deep cuts that were necessary everywhere. But I wanted to at least provide some context in that the red is the percent of VMT in each census division, and the black numbers are the percent of population. So down in the South, you all have 20% of the VMT with 18% of the population. And why I show this is that even if California goes to fully electric vehicles, we're still going to need electrification and decarbonization in the North Central and in the South and in the South Atlantic. It's impossible for any one region to do this alone. And that's for travel, and there's different urban and rural miles, and we're working on kind of that distribution now. But as you all know, electricity, besides ERCOT, electricity moves around the country pretty freely in the Western Interconnect and the Eastern Interconnect. And we could imagine doing this by NERC region. We could imagine doing this by time of day. We also probably want to deal with, with ISOs. I'll show you in a minute. But in NERC regions, CO2 intensity has decreased in all regions. And that's good news. And it actually, when we did this paper, we were pretty surprised on kind of the drop-off of coal up in the upper Midwest in substitute of really kind of gas boilers rather than NGCCs up there. But so there have been dramatic reductions in the average CO2 intensity across all NERC regions. We also, this is the chart I wanted to show about, we also have to think about in an ISO or an RTO, really that's the starting the level, even when we go down to the level of a balancing area authority, that's really the kind of the power analysis that we would want to do when if we're going to think about this as a national rollout plan. But in the end, all this kind of doesn't matter, like average versus marginal, ERCOT versus WEC. The electricity has to be at zero or pretty close to it. And once we kind of step away from that assumption at the kind of the national policy level, that's really where we have to think about going towards. Now, we track national emissions on our website, emissionsindex.org. All the data is and graphics are free. The code is available. It scrapes basically EPA SEMS and EIA 923 and 860 every month. Every 3 months we put out the data when they put out the quarterly data. We're about to put the next one out in 2 weeks or so. Now, I mentioned that there was a bunch of challenges. One of them was that we need to get electricity down to zero. But the other one is we have to get a whole bunch of EVs on the road. And one thing that we forget a lot in kind of tech is that cars are the second most expensive asset that most people own if they own a home. If they don't own a home, a car might be the first most expensive asset that somebody owns. And people hold on to cars for a long time. So an average car age is in the kind of the 12 to 13 year range, but there's a long tail. And so there's a decent amount of cars that, that are on the road 20 years or longer. The good thing about automation, as I mentioned before, is that we are going to save a lot of lives. Automation will save a lot of lives by stopping people from getting into fatal crashes by running off the road or going into their dead spot or hitting a car in front of them. That's amazing, and we should celebrate that every day. One implication of that is that this part of the curve, that 0 to 8, where cars generally don't, most cars generally don't exit, but the cars that do exit the fleet are leaving because they're totaled in a crash. We hope that those exits will go to 0, that nobody will crash, and the cars will just exit out of the fleet as they age out. What that does, though, is push this entire curve to the right, and it means that cars are probably going to last longer and take longer to exit the fleet. Now, we modeled based on global estimates and EIA's numbers. What if we said we only can sell EVs starting in model year 2020, right now? With natural attrition rates and kind of natural car buying rates, we wouldn't leave, that last EV wouldn't leave the fleet until 2050. That's if we started today, only EV sales. And that's because of that long tail, right? There's those cars that last 20 or 30 years, they're still around. They won't be driven that much, and they'll be antique cars. So a more realistic option is, well, what if we sold only EVs by, say, 2032, 2035, 2039? We could reach the targets that we outlined here, kind of 60-something% of the fleet as EVs by 2050 or higher, if we started selling only EVs in these model years. That's also surprised us. It's pretty late. If we could say we could wait till 2039 to sell all EVs and still reach a decent portion of the EV fleet by 2050, that's good. But it also means we don't really have a lot of room to play. We want to make sure that we have a decent amount of EVs in the fleet by 2050. The earlier that we start, the easier it is to maximize the likelihood that we'll have the amount of EVs we need in the fleet in 2050. Now, I didn't mention life cycle impacts here. We've done a lot of work on life cycle impacts of EVs over the years. Life cycle impacts include the material for the vehicle and the battery. When you build an electric vehicle, the battery, depending on assumptions, will generate about, let's say, 2 to 4 tons of greenhouse gas emissions. When you build the regular car, it's about another 6 tons. So all in, when you build a car, EV or not, let's talk in big general specifics. Making a car generates about 6 to 10 tons of CO2. When you drill for oil and you transport oil and you refine oil, when you move natural gas and coal around, or when you build power plants, all this has upstream impacts too, and we can calculate the changes in as you move from gas to electricity. Really, the bigger impact is the making of these vehicles, because it's copper, it's steel, and it's a lot of heat. It's plastics. It's things that generate GHG emissions. Let's say that we could drop this 7 to 10 tons of greenhouse gas emissions per car down to 3, which would be great. Hopefully we get it to none, but let's say it's 3. That means every 10 million vehicles, EVs that we would sell, or precisely EVs that we would make, generates a one-time pulse of 30 million metric tons. And we will need hundreds of millions of EVs on the road. Now, you amortize that over the lifetime of the vehicle. We understand all this, but this shows that we will need a concomitant decarbonization of the industrial sector, not just here, but in the countries that are part of the supply chain, in order to have kind of a large-scale global decarbonization effort. Now, we shouldn't wait to do that. An EV that goes on the road gets cleaner over time as the electricity sector goes down, carbon intensity goes down. but we still need to be cognizant of the fact that we haven't yet solved global industrial decarbonization, and we should be working on it. So what we have shown is that meeting a deep decarbonization target in 2050 is conditional really on getting GHGs from the electric sector down to zero, but also a fairly high amount of electrification for our different targets. Now, what would this mean for, say, a 2030 policy? Now, some of you might remember the Cash for Clunkers program, officially called the Car Allowance Rebate System. That had an average rebate of around $4,000 something in 2010 dollars. The total payout from that program was about $3 billion. If we restricted all new car sales to EVs starting next year, we could get half the fleet electrified by 2030, which would be great for the climate. That would leave a whole bunch of gasoline vehicles on the road. If we wanted to buy them off the road for the same amounts that we paid out under the Cash for Clunkers, now we're in the $500 to $600 billion range. Probably worth it, to be honest, depending on how fast we want a decarbonized vehicle fleet. But we shouldn't shy away from what the scale of that number is and the scale of this challenge. The paper that I've outlined here today is about to be published in Environmental Research Letters. Abdullah Al-Arfarj is the lead author with is the student, and my co-author faculty, Professor Mike Griffin. I'll leave you with one or two little slides here. That decarbonizing transportation with electricity is not just about cars. I mentioned micromobility and grocery delivery. We have these, maybe you have these in Austin, we have them in Pittsburgh. They're kind of running around delivering snacks and food. These might displace a car trip, right? So if you have a scooter or you have an e-bike and you have a micromobility or delivery, you might replace a car trip, and that might help reduce VMT. These also have emissions. We are leading a big project right now of understanding the impact of drone delivery. We have an initial paper that we published last year, or 2 years ago now, that said drones could have a lower greenhouse gas footprint than diesel trucks, even when you account for all of the packages that a diesel truck can carry. A drone is pretty light, and even though it's fighting gravity, it's small and it's electric, and it can move a small package pretty efficiently. The challenge with a drone is that you'll need lots of warehouses in an urban area. So these circles are the range of a small package drone. The range can go up as we get better battery and better drones, but now all of a sudden you don't need one distribution center to serve San Francisco Peninsula. You might need 4. And then in the entire kind of the Bay Area, you might need a dozen to several dozen. And that's because you'll need the same hard drive that I want to order from Amazon that's sitting at a distribution center kind of down here that gets trucked to me the following day. We'll need to basically, 4 of them will need to be sitting in separate warehouses ready to be droned out to a customer if kind of same day drone delivery is the kind of the goal there. So everywhere we look, we have to think about the systems impacts of transportation transitions, not just in the industrial sector, but also in the building sector. And the work that we're doing now is sensing up a whole bunch of drones that we've built and to carry packages around, and we're understanding kind of at the hertz level the energy use and the kind of the aerodynamics of what drone delivery does for energy use on the drone itself. It's strange that there wasn't a whole bunch of literature about this, I guess because nobody really cared, but it's been a lot of fun going out in the field and sensing up some drones. Now, in case you are wondering what Amazon is up to, this is from their patent that we saw online. When you have a floating warehouse, you could basically mobilize that warehouse over any place in the city. Somebody orders something, and you can send down a little glider drone. And so there are things out there that we haven't even thought about, but we are, as energy analysts, all of our jobs is to think about anticipating how to make policy under some deep uncertainty so that when new technology comes along and new assumptions change our models, we can rapidly adapt and adjust. So what I've talked about today is the synergy between all of these policy levers. We will need reduced VMT technology and strategies. This includes shifting to public transit, shifting to bikes and active transportation, shifting to micromobility, as well as increasing the amount of EVs on the road, increasing the total number of EV miles traveled versus the gasoline miles traveled, as well as reducing the electricity, the carbon sector well below 50 grams per kilowatt hour of CO2, and encouraging sharing and hedging against this kind of uncertainty between urban miles and rural miles. I hope that that we all can work towards the transportation decarbonization. We haven't yet talked about freight or air travel, which we're working on in separate efforts. But vehicle travel is going to be a big lift, and there are lots of opportunities for technology and innovation and policy to get involved. So with that, I thank you very much, and I'm very grateful for the time today. I'm happy to take some questions.
A round of applause. Thank you. A lot of good information and presentation material there. So we'll go around here with a couple questions. Go ahead and raise your hand. I'll come over if I see you again.
I have a couple of questions. Tesla already has numbers that its cars are 8.8 times as safe as the average American vehicle. And I was wondering, in your car removal scenario, have you considered the influence of insurance companies that it'll come a time when today's normal cars are much more expensive to insure than they are today, and therefore that is going to cause people, that's going to put pressure on people to junk their car, get rid of their conventional gas car much sooner than they otherwise would?
It could. I mean, and so there's a couple of points in here. So first, luxury cars in general are almost all safer than the average fleet. And so Tesla, we love Tesla, but there are, all these numbers need to go through kind of research and peer review like anybody else. And so their 8.8 number needs to be compared with the similar set of other luxury vehicles rather than a $14,000 ICE. Any luxury vehicle that has crash avoidance system is going to be safer. That leads me to the second point that you made about insurance and kind of the stratification. We need to make sure that as the transition happens, that it's safe and equitable for everybody involved, and that it shouldn't be unsafe to drive while poor. It is right now, and we want to make sure that that as a transition happens, we take policies to make sure that all vehicles have these collision avoidance systems. The insurance industry has been watching these issues really carefully. I think that they understand the changes that are going to come to their business model, but really, people hold on to things that don't make sense in terms of a discounted cash flow, because people are not rational. I do this for a living, and I'm not rational. Right? I mean, if we could calculate on a per mile basis, I probably should have scrapped an older car at some point in time, but we keep it until it dies. And so there's capital constraints that often stop lower income folks from making a new purchase, even though that new purchase might be better for them over some discounted cash flow horizon.
But you're assuming they're going to purchase a car with the advent of robotaxis, that we don't need to own a car.
Maybe. I mean,
at least for people in urban environments.
Maybe somebody still wants to own a car. Maybe somebody is not served well enough in the rural area where they are, where the robotaxi is not going to serve them. We hope that robotaxis serve as many miles as possible, but I think that the default assumption that nobody will own a car is premature.
Well, not nobody. Obviously, the rural areas will be the last to have the opportunity not to own a car. Just one other comment. The advent of Tesla's Semi and other competitors' semis that are electrically driven is going to solve that diesel problem for everything, really a substantial reduction in the use of diesel fuel.
We hope so, and we were really excited when the Tesla Semi was unveiled. We need to see these vehicles get on the road and fast. As you might know, a truck glider stays on the road for a long time. The engines are rebuilt. It's a long-term piece of capital, and the capital cost of a new Tesla or EV Semi needs to drop precipitously in order to change the current business model, and we hope that they do.
Thanks, Costa. Let me follow up with a couple life cycle questions before I pass it over to another one. So your chart in there, if you had a zero carbon grid, there's still a non-zero emissions associated with the cars. Is that just manufacturing and life cycle of the cars that was on that factoring into there?
The emissions all the numbers that I presented for this paper, in the base cases, that assumes combustion only at both the power plant and the ICE tailpipe. So we didn't include manufacturing of the vehicle, we didn't include manufacturing of the petroleum products, and we didn't include the upstream impacts of the electricity sector. All of those would add a decent amount. We're working on a separate paper that will understand the kind of the trade-offs of those. But we wanted to basically present a transportation-only base case to be comparable with EIA and other projections. As you include life cycle impacts, the amount of EV requirements that you have just get higher.
Right. On the insurance, and then I'll hand it over to another question. It started making me think how much you had a nice slide earlier summarizing different kinds of social cost impacts of, I guess, vehicles in general. A lot of the mass of a car is to keep a human safe. So if you don't put humans in it, you lower the mass. So have you specifically thought about that and some of the numbers and life cycle and CO2 of making cars, and anything to say on that?
Absolutely. And so there's a bunch of literature about lightweighting and considerably reducing vehicle mass in different ways. Some of that is with carbon fiber, some of that is with plastic, some of that is with aluminum. One of the challenges of extreme lightweighting, where we would like to get to, is that there is increased risk of injury as long as you're in an environment that has other heavy cars on the road. So we could imagine a robotaxi fleet that's operating in lower Manhattan or Manhattan below Central Park or even all of Manhattan. That is, if the whole zone is light robotaxis only, now you can dramatically increase the efficiency of the robotaxi by dropping the weight a whole bunch. But if you wanted to have a mixed fleet of robotaxis that were really light and kind of 3-ton vehicles, there would be an increased safety risk to the robotaxi occupant. We have been modeling this because you also could, my colleagues have been doing some work on optimizing the size of these. If you have a robotaxi fleet and you call for a one-person taxi, you could send a little pod. If you have 4 people, you could send a bigger car. Right now, we send the same car for every demand, and that's efficient use of vehicles, but not an efficient use of energy.
Oh, thank you for your excellent presentation and your insights. A number of questions. Try to ask this from anyone who is looking at the different trends for batteries. We've seen a faster decline in battery costs, dollars per kilowatt hour, than was expected over the past decade. Just wanted to get your view of where you think the range that, and it'll be an average and it'll be lumpy, for example, of compound average cost decline rate over time, 5, 9% versus the 14 that we've seen over the last decade on that. So where do you see that going? Secondly, CMU is a powerhouse in robotics. I was on the UT 2007 DARPA Urban Challenge team, and you all, I think, won it or came in second from Stanford. And so it's very interesting to hear the latest views on LiDAR versus no LiDAR, Tesla being in the no LiDAR camp, and CMU at that time. Even we had this $100,000 Velodyne spinning on the top of our vehicle. So you had mentioned, the power drain of LiDAR plus the cost of that. Just wanted to get your view if you're in that. Third, a year or two ago, we had a gentleman from the Carnegie Endowment that presented at the same forum. And it was very interesting because he was talking about the different emissions from the different sources of oil. We always tend to see analysis that says, well, here's an ICE versus an EV, and then here's the regionalization from the different sources of the grid mix for that. But I've never seen anyone take that the next step forward and regionalize the oil supply, which would be very challenging because tar sands or oil sands are far more carbon intensive. So just wanted to plant that seed, maybe if you're pursuing that to get a greater granularity in the comparison.
I appreciate the comments. Thank you so much. The first on the battery cost, that has really surprised a lot of us in how fast that the costs have come down. I think the challenge now, and I haven't done a recent paper on this, but my colleagues Jay Whitaker and his student have done a couple papers on where costs could go from here. Now, we've already kind of gone down the steep part of the curve, and at some level you're going to approach basically commodity pricing of the materials themselves. So at current chemistries with the copper, the nickel, the aluminum, the manganese, cobalt, at some point you're going to just approach commodity plus assembly. Now, I don't think we're there yet, but really the percent cost decline is interesting. I think what's more interesting is, can we get it to $50 a kilowatt hour, right? I mean, and if it goes from 50 to 47, great. But let's get it to sub 100, sub 50, close to that, and I will be very happy about the prospects for EVs. And I still think that there's great prospects for them going forward, obviously. But there's a whole bunch of companies working on different chemistries. I think that should continue. There was a view from a bunch of OEMs a while ago that lithium wasn't it. They kind of got caught flat-footed, I think. But at the same time, they weren't completely wrong. That lithium as a kind of lithium, manganese, lithium, nickel chemistries are not that great for scaling and cost reduction and lifetime going forward. And so I would love our material scientists at UT and CMU to come up with kind of some magic battery that is cobalt-free and has a chemistry that has long longevity and cycle life. Your second question was like the LiDAR versus object recognition war. I don't have a dog in that fight. I analyze each of those technologies, and I'll tell both of their inventors that they're not good. But really, neither of them have really. They've both progressed amazingly. Neither are really inspiring the type of confidence that I want as a safety critical function yet, and we're getting there. I don't have a good prediction of which one is going to win. Right? This is, knowing what we know now, we probably could go back and see that Westinghouse and Tesla were going to win versus Edison. I don't know if we can do the same with LiDAR versus cameras. And your third question was about the difference in oil. And we know those authors from Carnegie Endowment. One of them was our alum. And I think that would be interesting, especially as the mix changes with kind of West Texas oil kind of coming online, with Venezuela going down, with tar sands going down. It's not going to change the answer dramatically unless we start using a whole bunch of more heavies. So basically, the light part is going to get a little bit better. If we start using a whole bunch more heavies, it gets worse. But no way, even with the best light crude, are we going to be able to beat, a Tesla. It's just on a clean grid.
Thank you.
Thanks. On the LiDAR and other methods of autonomous vehicles, do you have a number off the top of your head for sort of electricity per mile or something like that?
It's
or range?
It's not that much, but we did a kind of a rough cut in our paper. I'll defer to my colleagues who have another paper that's coming out. I'll get that number and get it back to you, Carrie. I don't know what it is. The GPU and the trunk is really the energy hog. Right? And so as the energy use of computing goes down, that also is a benefit to these systems.
Yes, an earlier presenter at this forum was from Toyota, and he noted that Toyota is building an entire series of vehicles from sedan to long-haul truck, all powered by hydrogen. And do you see between now and 2050 that hydrogen-powered vehicles will be a significant factor in decarbonization?
Thank you. So we did a paper last year on the future of fuel cells. We did two papers, one for stationary and one for vehicles. Both of them looked at cost and for the different components of and the performance of these components. You know, I went into this with an open mind, and I came out with really being more excited about fuel cells for stationary applications than I am for mobile applications. I know Toyota has been kind of a 20-year project of making hydrogen happen, and I hope that it happens. But the moving parts, the complexity of the fuel cell itself need to be improved. And then the whole source of hydrogen. So if I'm going to, making hydrogen with natural gas and then taking that hydrogen and running it through a fuel cell to make electricity to run basically in electric vehicles, what's happening is, to me, it's like washing your dishes with single malt scotch. Like, it works, but I'd rather use that hydrogen for something else. And the carbon footprint of making hydrogen from natural gas is not great. And so I might just rather burn the natural gas and make electricity, store it in a battery, and run the vehicle that way.
Costa, I think that's all we have here. So thank you very much for an entertaining and a very informative, I think, presentation, and very well done presentation on electric vehicles and autonomous vehicles. So let's give them a hand remotely. Thank you again.
Thank you so much for having me. I'm always impressed with the scholarship of the UT Energy Institute and the UT students and faculty. Thank you so much for having me, and thanks again to Carrie and Josh. Appreciate it.
Yes, as we are as well at CMU, and looking at the data you make available as well. So it's great that the work that y'all do. Thank you very much.
Thank you.